Hi, I'm John Barron. I'll be presenting this work on behalf of my collaborators. There's been a lot of recent progress in computer vision and computer graphics on using simple, fully connected networks, also known as multilayer perceptrons or MLPs, to represent 3D objects or scenes. For example, an MLP could take as input some low-dimensional vector, like a 3D coordinate, and output a binary value indicating whether that point lies inside or outside the 3D object. This sort of network is fundamentally a continuous representation, and that means it can be densely sampled to recover the encoded shape. Note that for this sort of task, we're trying to get the MLP to represent a complicated function on a low-dimensional domain, and this is different from most typical uses of neural networks, where the input is usually a very high-dimensional vector, like all of the pixels in an image. A simple example of this sort of network is just using an MLP to represent an image. Here, the input to the network is just a single 2D pixel coordinate, and the output is a single RGB color. Here's what training looks like if you try to train that sort of MLP to just memorize a single image. As you can see, the network struggles to recover high-frequency details in the image, even though the MLP has more weights than there are pixels in the image. This isn't just a problem for training MLPs to represent images. You can see this effect when training MLPs to represent other high-frequency functions on low-dimensional domains like 1D curves and 3D shapes. In this work, we present a simple technique that fixes this problem. Instead of just inputting the low-dimensional coordinates directly to the network, we first pass the coordinates through a Fourier feature mapping, which looks like a set of randomly scaled and rotated sinusoids. And this allows us to control the frequencies that these MLPs can represent in practice. With this simple trick, the MLP is able to quickly recover the fine, high-frequency details in this image. In the paper, we use tools from the neural tangent kernel theory to show that using Fourier feature inputs causes the MLP to perform interpolation between the data points used for supervision, and that the frequencies of the sinusoids directly control the smoothness of the MLP's interpolation kernel. A standard ReLU MLP has a very wide kernel that leads to an oversmoothed function. Typical ML problems like classification with high-dimensional inputs actually benefit from the smoothness of standard networks as it prevents overfitting. But in our setting, using Fourier features is critical for allowing the network to represent higher frequencies. And if we increase the frequencies of our Fourier feature mapping, the MLP better fits the training points, though as you might expect, increasing the frequencies even further leads to overfitting. This simple technique of using Fourier features with an MLP is surprisingly effective for a wide variety of low-dimensional problems, like representing 3D shapes, solving inverse imaging problems like MRI reconstruction, and reconstructing a neural radiance field from images. In contrast, using just an MLP without Fourier features works poorly for these tasks. Thanks for watching. Please check out our paper and website for more examples and code.